Okay. Apart from estimating range or velocity, a radar has an important objective, which is detect. Detect means take a decision. So for every resolution cell, for every possible position in the area which is surveyed or controlled by the radar, we have to indicate if we have a target or not. And that's a binary decision, similar to detecting bits in a digital system, communication system. So we have actually, in the real world, we have two possible hypotheses. We can have a target, or we may have no target in a certain position. And the radar has to take a decision. D1 will correspond to indicating we have a target. D0 means the radar decides there's no target. Of course, we would like to be always correct, but sometimes we will have errors because the target, we have to take decisions from observing the echo signals, which are corrupted by noise and so on. So the probability of detection is actually the probability of deciding we have a target when we really have a target in a certain position. The probability of missing the target is deciding D0 in the same H1 situation. We have a target and we lose it. And there is another important parameter, which is the probability of false alarm. A false alarm in radar means we have no target and the radar decides wrongly, interprets we have a target at a certain position. These probabilities can be characterized from the characteristics of the radar, the power of the signal, of the received echo, and so on. And this is our job now. So let's do some characterization of these probabilities. Probability of detection, probability to be right when we have a target, probability of error, which is probability of false alarm. Probability of miss is easy to calculate because it's 1 minus PD, because that's the other situation, the other possibility of when we have a target. So probability of miss is it is immediate if we know the probability of detection. So the two important ones is PD and PFA, detection and false alarm. Now, how is the radar going to take the decision? Well, the radar, the only thing that has no crystal ball. Of course, the only thing is we can observe the signal at the end of the receiver, the echo signal. So in the hypothesis H0, we don't have a target, so we will have only noise at the receiver output. When we have a target, otherwise, superimposed to the noise, we have an echo signal. The decision will be based on the observation at the receiver output. Now, the process of decision is almost always based on a threshold level detector, which is depicted here by this subsystem here. When we have, for example, at the end of the receiving chain, we obtain the echo amplitude, this VT, and we compare with a certain decision threshold level. So let's assume we transmit a pulse, and now we operate the radar receiver, and we are listening to the echoes, possible echoes, and we get this signal in blue. And we set the threshold level at this constant value. So here we have two targets. They provide peak echo signals at the output of the matched filter. And we are fortunate in these two cases, so we detect correctly the targets. In here, there is no target, but the noise actually, after the filter actually overcomes the threshold level, so we get here a wrong detection, that's a false alarm. And this very small target here is not enough to actually reach the threshold level, so we don't detect here. So we see here two correct detections and two errors, one false alarm and one miss. Okay? Now, how should we adjust this threshold parameter? Of course, if we adjust the threshold to a low level, the probability of detection will increase, of course, but also the probability of false alarm will increase, which is not very nice in a radar. False alarm is something we have to avoid in a radar. Otherwise, if we increase the VT parameter, then the probability of false alarm will decrease, which is good, but we are also going to lose targets. So the probability of detection is going to go to a lower value. So now, how to adjust the VT? Well, there are several ways to do that, but in radar, what is normally used is the so-called Neyman-Pearson criterion. This is actually related to the cost of the errors, of detection errors. So the cost of the false alarm for a radar is huge. It can result in a distraction of the operator. It can result in a very wrong action, like, for example, sending an aircraft or firing a weapon to a wrong position. So in radar, false alarms are really costly errors, so we are going to actually limit them as much as we can. So VT is normally set for reaching a very low probability false alarms, typically 10 to the -5, 10 to the -6, up to 10 to the -8. This is the probability of acceptable false alarm for a radar. Then, after setting the threshold, we dimension the radar, which means transmitted power, gain of the antennas, maximum range, and so on, in such a way, signal-to-noise ratio will be enough to satisfy the required probability of detection that has been set by the radar user. This is how the radar design is performed. Now, how to quantify these parameters? Okay, let's look into the statistics of both the signal or the noise when there's no target, or the noise plus echo signal when we have a target, in order to compute the probabilities. So, okay, let's take a look of the output of the receiver. Here, a receiver typically ends with an IQ detector, which obtains the real and imaginary part of the echo signal. If we want to take the envelope, we can compute the square root of this. This is the fasorial representation of a signal, real, imaginary part, and then the length of this phasor is what we obtained with the envelope detector. This is actually equivalent to an ideal diode, if you want. That's how a professional system obtains a signal envelope. A low-cost signal could use a diode, which has certain limitations to do that. Now, let's take a look at the statistics of this envelope. Actually, if the radar is processing noise, these IQ components of the noise are Gaussian. So this is the Gaussian PDF of the I, or real part, and Q, imaginary part of the echo. Both these components are Gaussian. They have the same noise variance, sigma n square, and that's the noise variance is related to the noise power at the receiver output, and multiplied by the impedance, because the variance is the voltage variance is the power multiplied by the impedance. And this is related, for example, if we express this without the gain of the receiver, with a normalized gain receiver, this is just the Boltzmann constant multiplied by the total temperature of the system, antenna temperature plus receiver temperature, the bandwidth of the receiver multiplied by the impedance. If you have a gain, you have to add a gain here into this expression. Now, if we obtain the envelope of this signal, the envelope has a PDF, which is a Rayleigh. It is this expression here, when this sigma n squared is still the noise variance at the receiver. So the shape of the Rayleigh is like this, and then when we set the threshold at this point, this area, which is equal or higher to the threshold, it is actually the probability of false alarm. So this is how probability of false alarm is computed, and this allows setting the VT to the appropriate PFA value we want. Now, what happens with the target? Well, in the target we have the H1 hypothesis, which means at the receiver output we have noise plus echo signal. In this case, the Rayleigh statistics is modified by the presence of the target, the presence of the echo, and we get a new PDF, which is a Rice statistic, a Rice distribution, which is actually contains still an exponential term, but also a modified Bessel term here, and it depends on both the noise variance and the echo amplitude. So the echo amplitude can be related to the signal-to-noise ratio of the radar with this expression here. So, and this is the shape of the Rice. Actually, the lobe gets actually moved, shifted towards the right position. So if we use the same threshold as before, VT, now the probability of detection is the integration of this area, this blue area, and in these ways we can compute both the probability of false alarm and the probability of detection. So again, using the Neyman-Pearson criterion, PFA determines the setting of the threshold, and then from the minimum requirement of probability of detection, we can compute, or we can estimate what is the minimum signal-to-noise ratio that we need in order to obtain this PD parameter which is required. This is true, all this analysis is true in a simple situation when the noise at the receiver is a constant, is a stationary process. What happens in the first 20, 30, 40 kilometers around the radar is that we frequently have also the interference of clutter. So mountains and non-decided objects, forest, sea clutter or land clutter actually provides an interfering echo signal, which is also modeled as a statistical process, and this means the interference in this case is not stationary. So in this case, a constant threshold level would not be appropriate, and then we have to modify the detector in order to be adaptive to the level of interference. We are going to see this in the CFAR detector part of this presentation of this course. Now, still in the stationary noise-limited situation, we can compute the probability of false alarm in this way. This exponential simple expression will give us the result. In the case the target is a statistic target, for example, a swirling target, in the case the swirling is 1 or 2, the target was considered to be Gaussian. So real and imaginary part are Gaussian processes like the noise. So in this case, we can reuse the previous expression, the previous integration, just by substituting the variance, because now we have a new Gaussian process, which is the addition of two processes, the noise process plus the echo process. Both are Gaussian, so we can just consider a new Gaussian process with the addition of power as a variance. So in this case, this can be expressed with this term, which has into account the signal-to-noise ratio of the signal, of the echo signal delivered by the target. So we get the same or similar expression, which contains also the variance of the noise, but also the signal-to-noise ratio. So in this way, we can compute both probability of false alarm and probability of detection when the target is swirling 1 or swirling 2. If the target has a different statistic, then the calculation will be different.